Okay, hi everybody. I'm going to get started. I fix my little fan that fell over. Keeps my computer nice and cool. All right. I do want to say that some of you haven't handed in the graded assignment 5. So you need to get these in. Okay. And some of you still owe me the exam, and you need to communicate with me. All right. And I need to do that right away. All right. So I want to get back to what we're doing. So last class, I started unit 6, which is our second to the last unit. It's on acids and bases. And what I said, just sort of a summary, because I didn't cover very much last time, I talked about strong acids. And I said that strong acids, I use the term dissociate or ionize completely. And what that means is, for example, if you have hydrochloric acid, which is a strong acid, and you put it in water, it completely gives you H+ and Cl- ions, completely. It doesn't stay as HCl at all. This essentially goes all the way to the right, which we say, the expression we used in lab this week, it goes to completion. All right. Then I talked about, and there's only 6 of them, and I told you what they were last time. And then I also introduced the idea that there are weak acids, okay? And these only dissociate a little bit, or only ionize a little bit, which is to say that they're involved in, that they, when you put them in water, there is an equilibrium that is set up between the weak acid. So for example, we have CH3COOH, which is acetic acid that I mentioned last time. It's in an equilibrium in water with CH3COO- and H3O+. And not only is it an equilibrium, but it is an equilibrium that lies really quite far to the left. It favors the undissociated acid. There's more of that in there, definitely, way more than that. So there's more of this and much less of this at equilibrium. So while we're on the subject here of acetic acid, this is like the prototype acid that I use for lots of examples. And it's very, it's ubiquitous. I mean, it's everywhere in general chemistry. As you know, I hope, it's the main, it's the acid component in vinegar. But there's many ways to write it. And I want to go over some of those ways. I think I probably did this last time, but I'm going to do it again. So here's the CH3, COOH. And so the equilibrium, this goes to CH3, C double bond O, O negative. So the 2 electrons from here ends up on that oxygen. And then you have H+. Okay, now there's many different ways that we chemists, many different ways that we write acetic acid. And this is one of them. And this is what we call the acidic hydrogen. This is the hydrogen that is released. I talked last time about how these bonds here, these are not polar, these are non-polar bonds, and how the more delta negative, delta positive that hydrogen already is, the more easily it is released. And so you really couldn't have a hydrogen on a non-polar bond and have it be acidic. But I also talked about how ethanol doesn't have this double bond to oxygen, and ethanol is not acidic at all. And that's because this oxygen here makes this a carboxylic acid, and it actually pulls electron density away from the hydrogen. So another oxygen, another highly electronegative oxygen there really is what makes the C double bond O, OH group. That's what we call a carboxylic acid. And you will see that a lot more if you take organic chemistry. But anyway, I wanted to tell you that the other ways that we write acetic acid, we write CH3, COOH, that's one of them. We also often write this, we take the acidic hydrogen, that's this hydrogen right here, the one that's attached to, the COO and then that H, and we put it at the beginning. Okay, very often we do that for acids, and then we just sort of lump the rest into a formula, which would be C2H3O2. So we take the acidic hydrogen and we put it at the beginning. And we also, with acetic acid, we have another like affectionate abbreviation that we use. And this is actually the way that I mostly write acetic acid. And that is we take and call this whole part of the molecule here, right? That's the part that is that everything except that H plus that gets released. This is the acetate part. This is actually the acetate ion with an H plus on it, becomes acetic acid. So this is like an abbreviation for acetic acid. So this is just acetic acid, sort of shorthand. And it's really a kind of a nickname. And all of these undergo the same reaction. There's an equilibrium, which, you write it this way. I just want to tell you that it mostly goes back. It doesn't go forward that much, but we don't write it that way. We just write it like this. And you can see here, this is CH3, this thing here, COO minus. This, by the way, is the acetate ion. Okay, and of course, then we have the H plus. And I would write it here. This H is the one that goes away. That's the acidic hydrogen. And so the rest of it, again, this is acetate ion. And here I would write it as OAC minus plus H plus. Again, this is acetate ion. So these are, 4 different ways to write the exact same chemical reaction. And I just want to bring them to your attention because, you'll see the way acetic acid is written in different websites, different books, and some of them use this notation, some use this, some use this. So I just want you to know, but I want to tell you that my choice is generally HOAC. So if you want to find the molar mass of acetic acid, you cannot use this formula, because if you look up this, AC might be an element, but it's not going to give you the right molar mass. This is the formula. You have to use one of these other formulas if you wanted to calculate the molar mass. All right, so that's basically all I have to say for now about acetic acid. In fact, I want to talk about bases a little bit. So what is a base? And what I said last time is that these are hydroxide ion producers. Okay, that's sort of the simplest definition. And I'm going to tell you in just a few minutes a little more complicated definition that brings in more chemicals, brings them into the fold of bases. But anyway, so what is the simplest kind of base? If you take and dissolve sodium hydroxide, okay, this is a soluble hydroxide. Many hydroxides are not soluble, but this one certainly is, okay? And actually, I think Drano is mainly sodium hydroxide. So it's a soluble ionic compound. And so when you put it in water, it basically produces the 2 ions. And so you see that it has produced hydroxide. So sodium hydroxide is a base. And acids and bases react in an acid-base neutralization reaction, which I'm sure you learned about last semester. Acid-base neutralization reactions. And honestly, what happens is the acid produces H+, the base produces OH-, and the essence of an acid-base neutralization reaction is the H+ and the OH- coming together to give you none other than water. Okay, so you might have some other counter ion. If you had HCl, you'd have chloride as a spectator ion. If you have hydroxide, it had sodium, then sodium is there. And so, but they're just watching. They're not really participating. Okay. All right, so now we need to go a little bit of a level up. We need to go a level up in sophistication. So I said that acids are producers of H+. They generate H+ in solution, and bases generate hydroxide. But the definitions of an acid as an H+ producer and a base as a hydroxide ion producer, these are very limited definitions. And they don't tell you anything about the chemistry that's involved with these, with how these ions forming. So there is a somewhat more sophisticated definition that somebody actually gave me yesterday or Monday, sophisticated definition of an acid and a base. And that more sophisticated definition is that an acid is a proton donor. So instead of just saying it produces H+, it says it donates H+. It's actually talking about what the acid is doing instead of what it is. And the base is a proton acceptor. And these are much more interesting and really not as limited. And I'm going to give you an example in a little while of why the definition of a base as a hydroxide ion producer is limited. But what I want to tell you first is that this definition lets us think about the whole of acid-base chemistry a little bit differently. Let's start with something simple. Let's think about HCl is an acid. So if you think about an acid as simply simply producing H+, that doesn't really tell you what HCl does. It's like saying, oh, HCl just falls apart and gives you H+ and Cl-. Okay, so the first definition, that HCl is a producer of H+ would mean, okay, HCl just breaks apart and gives H+. So that's one way of looking at it, okay? But another way of looking at it that uses the other definition is it doesn't just fall apart, is that HCl the other way, so this HCl as a proton donor, okay, that you would say that HCl reacts with water and donates a proton, an H+, to H2O. So it actually kind of tells you what HCl does. Here's HCl, and here's water. If it donates a proton to water, okay, donates proton, and of course a proton is H+, then what you end up with is, okay, so now the HCl doesn't have the H+ anymore. So all it is Cl-, and the proton attaches on to a water molecule, which we know it does, and forms this hydronium ion. and I draw a single arrow here, this is a one-way arrow. That's because HCl is a strong acid. Okay, remember that. Okay, so now if we summarize what happens, we would say this, we'd say HCl donates a proton to water. So therefore, of course, HCl is a proton donor. So it's an acid. Then we would look at this and we would say, okay, water is accepting a proton. That's exactly what it's doing here. It's accepting a proton. Okay. Wait a minute. If water is accepting a proton, then what is it in this reaction?
A base.
It's a base. So water acts as a base here because it is a proton acceptor. Okay, now I'm going to leave that for the minute. We're going to come back to that. But I want to tell you something else, that a very well-known weak base, I haven't said anything about weak bases now, but I'm going to tell you now. The most well-known, the prototype weak base in Chem 104 is ammonia. And you should know, you should memorize this formula. NH3 is the formula for ammonia. Now, if you look at NH3, okay, that's just, you know, nitrogen. It's got a lone pair. It has this structure. And if you look at that NH3 and you say to yourself, well, where the heck, how can it be a base? Why am I saying that? How can it be a base? Where's the OH minus? If a base is a producer of OH minus, I can't see just by looking at NH3 how it could fall apart and give me any OH minus. So the hydroxide ion producer definition, you know, forms OH minus. It doesn't really work for ammonia. But that's not what happens with ammonia. Ammonia definitely is a base, a weak base, but it reacts with water. Okay, so the question is, where's the OH minus? How can it be a base? It reacts with water and acts as a base. So as a base, it would accept a proton from water. And some of the time, but not very often, so this is another equilibrium where it's really kind of heavily favors the reactant. So it doesn't happen that often, but look what happens when a proton, NH plus, goes from H2O to NH3. What do I end up with? What does this become after that happens? Is it still NH3? How many hydrogens will it have now?
It'll have 4.
It'll have 4. Yes, 4. Will it still be neutral? No, because it accepts a proton, and a proton has a positive charge. Okay, so I took an H plus away from water here. What stays behind? What is left? When you remove an H plus from H2O, what do you have left? OH minus, exactly. Okay, there's your OH minus. So if you were envisioning a base as just sitting there and forming OH minus, like sodium hydroxide, you know, it sits there, it dissolves, it forms OH minus. That's great for sodium hydroxide, but that definition doesn't work too well for ammonia. For ammonia, you have to realize that ammonia accepts a proton. That's an H plus from water. Okay, and it does, by the way, once in a while, because this is an equilibrium, and it does this only a little bit because it's a weak base. So NH3 accepts a proton from water. This forms NH4 plus, which, by the way, we call this ammonium or ammonium ion. And the other product is OH minus. So here, in this reaction, water acts as a what? Water is donating a proton. So what does that make water here?
The acid.
An acid. That's right. So here we are. It's really like the first full day of talking about acids and bases. And I think already it's clear why acids and bases, why their study of acids and bases can get complicated. Okay, because here I have water acting as an acid. So I'm actually going to write acid underneath it, right? And we have NH3 that's a base, okay? And if I go back to what I had before, here I have an acid, HCl, and water is acting as a base. So water, you know, it acts differently depending on who it's hanging out with. You know people like that? People who act differently depending on who they're with? There are people like that. Anyway. Okay. So let me write that down. Wrong page. So water can act as a proton donor, an acid, when in the company of proton donor would be in the company of a base, and it can act as a proton acceptor when in the company of an acid. Okay, and actually the term for that is amphoteric. And not just water, many substances are like this. Which is one reason why, you know, there's so much richness in this subject. Okay, so going back to ammonia, we had this equation, this chemical equation for ammonia reacting with water. We had this proton donation, H plus. So the arrow here just indicates the direction of the proton. We have a reaction like this. It doesn't go forward very much because ammonia is a weak base. Okay, so we know that ammonia is the base and water is acting as an acid. Okay, but this is a double arrow here. Okay, and you can see that this reverse arrow is the more important of these reactions. Okay, so if we look at what's happening in reverse, we see that what's happening here is that NH4 plus is donating a proton to hydroxide. And when it does that, it forms water. Okay, hydroxide accepts it. So hydroxide here is a base, right? Because see, the protons going this way. This is a proton acceptor. And this reaction, because it's the reverse reaction, happens much more than the forward reaction. And in that reverse reaction, ammonium is acting as a proton donor. So this guy here, ammonium, is really an acid, and hydroxide is a base. But what we do is we label this ammonium here as the conjugate acid. It's the conjugate acid is the conjugate acid to the base ammonia. Hydroxide is the conjugate base to water. So this is conjugate base. And usually I just abbreviate these, Ca and Cb. So here we have the base ammonia reacting with water, which is acting as an acid, and a little bit of the forward reaction. But the backward reaction, which is even more important, is another acid-base reaction. The acid is ammonium, which is what we call the conjugate acid to ammonia. And the base is hydroxide, which is the conjugate base to water. And so we come up with this idea of conjugate acid-base pairs. Okay, so for example, we have ammonium and ammonia. Here's the conjugate base, and here's the conjugate acid and the base. And what do they differ by? How does ammonium differ from ammonia? What would one of them have to lose to be the same as the other one? What would ammonium have to lose to be the same as NH3? This is what conjugate acid-base pairs always differ by. They differ by an H+, the thing that gets donated or accepted. Okay, so in ammonium and ammonia, these are conjugate acid-base pairs. You can see that ammonia doesn't have the H+, and ammonium does. The acid in the pair, the acid of the pair has the H+. The base of the pair does not have the H+. So this is without the H+, and this is with the H+. Okay. And the same is true if you think about water and OH-. Hydroxide is the conjugate base of water when water is acting as an acid. So what do they differ by? An H+. The base doesn't have it, right? The base does not have the H+. The acid, water, acting as an acid, has the H+. Okay, they differ by an H+. So you always see that with conjugate acid-base pairs. Okay. So I'm going to move to activity 1 from unit 6, which I have on the next page, I think. Yeah, here it is. Okay. So in this exercise, what we're going to do is we're going to draw an arrow. I don't mean the arrow for the reaction. I mean the arrow either going this way or this way that represents the direction of the proton donation, okay? Direction of the proton transfer. And we're going to do that the same for the reverse reaction. And this says, if there is one, okay, when would there not be a reverse reaction? That would be when there's a very, very strong acid, because reverse reaction doesn't happen. It's only a forward reaction. I'll show you as we go along. If a single arrow is drawn in this exercise, it means that there's a strong acid, because strong acid fully dissociates. And then we're going to be labeling the acid and the base on the left side. That's on the reactant side. And then we're going to identify and label the conjugate acid and the conjugate base on the right side, on the product side. Okay, so if we start with this first example here, we have water and HNO3. And you notice that this is a single arrow. So the single arrow tells you that HNO3 is a strong acid. And it's one of the 6 strong acids that I pointed out yesterday or Monday. Okay, so let's see. So now I want to draw an arrow indicating the direction of the proton transfer. Well, you could see that this ends up being NO3 minus over here. NO3 minus, to write it a little darker. H3O plus and NO3 minus. Okay, so the direction has to be this way. The proton transfer, the H plus, goes from the acid, which is the proton donor, to the base. Water is acting as a base, proton acceptor. Okay, and when it does that, you could see that the H2O becomes H3O plus, and the NO3, the HNO3 loses a proton, it's NO3 minus. So it says, do the same for the reverse reaction if there is one. Now, in this case, is there any reverse reaction? So the reverse reaction would be, if it happens, that a proton would get donated that way. Okay. So does anybody know the answer to that question? Is there any reverse reaction? Well, I mean, take a look at the arrow, right? It's a single arrow. So no, that's right. There is no reverse reaction. And that's because nitric acid, HNO3, is a strong acid. So the thing is, this is the base, this is the acid. Even though this reverse reaction does not happen, we still refer to nitrate as the conjugate base of HNO3. So we still use the term conjugate base for nitrate, even though the reverse reaction doesn't happen. It is still an HNO3 without an H plus. It's still, it's still a conjugate base of NO3 minus, and H3O plus is always the conjugate acid of water, differs by an H plus. Okay, so that's the first one. Let's take a look at the second one. So here I'm using the very typical example of acetic acid, HOAC. Okay, so this is a reaction of the weak acid, acetic acid, with the weak acid ammonia. It's a double arrow reaction. So in order to get acetate here, the hydrogen, this H, this proton, would have to move that way. So the proton donation would be like that. And you end up with acetate ion and ammonium ion. So this is donating a proton. So this is the acid. This is accepting the proton. So this is the base. And in the reverse reaction, so how could we get back to that side? We would have the OAC minus accept a proton. So ammonium here would be the acid, the proton donor, but we would call it the conjugate acid. It is the conjugate acid to ammonia. And acetate is the conjugate base to acetic acid. So that's how we would label these in this equation, if you're ever asked to do that. Here's one that's a single arrow. And that's again, because this is a strong acid. This is a very strong base too. So for both reasons, this will only go in one direction. And you can see that to form water, you have to take a proton from the H2SO4. So here we have a situation where this is called a diprotic acid because there are two hydrogens and loses one, forms water. And now when you take away one hydrogen, one H plus from that H2SO4, you end up with HSO4. You lost one of the hydrogens, but you also lost a plus charge. So it retains a negative charge there. So don't forget about the charges. Students sometimes will write these things and just say, oh, I can't deal with those charges. If something loses plus, it becomes negative. That's all you have to know, really. So here the proton goes that way. This is the acid. This is the base. And which way will this reaction go? Will it go like this first, or will it do one, or will it do two? Which way is the arrow going to go here? And there's a third answer. Does it actually go? So let me see if somebody answered this question. No, it doesn't go. That's correct. So I'm just going to draw it as a dotted line because it doesn't really happen. It does not happen. Okay, but if it did, it would go that way. Okay, the reason it doesn't happen is because H2SO4 is a strong acid, but we still call HSO4 minus the conjugate base to H2SO4. And this is the conjugate acid to hydroxide. They differ by an H plus. So we have base, acid, conjugate base. Okay, but this doesn't happen. Just like I should draw a cross here, this doesn't happen either because they are strong acids. Okay, so now I have an example where I have a weak acid because it's a double arrow. And you can see that to end up with F minus fluoride ion, it must mean that this proton was donated and this becomes water. So this is the acid. It is donating a proton. So H plus is going that way, donates the proton. This accepts the proton, that's the base. And now, which way would the arrow go? One or two? Two. Yes, it has to, because you have to end up with HF over here. So the proton has to go back that way. That makes F minus a base. It is a conjugate base of HF. And water is acting here as an acid. It's the conjugate acid of OH minus. It differs by a proton. Okay. All right, now here's another one with, this is a triprotic acid, where there are actually 3 hydrogens that can be donated. This is a very important acid in biological chemistry. It's one of the buffers in the body is based on phosphoric acid. This is pretty strong for a weak acid. It's a weak acid, but it's one of the stronger ones. So it donates a proton. And you could see that it's becoming H3O plus, so it had to receive that H plus. Water is acting as a base. Phosphoric acid is acting as an acid. It's called phosphoric acid. All of these names, by the way, you could find them in the acid dissociation chart here, which I showed you. So here's phosphoric acid. Okay. All right, that's all I want to say about that right now. All right, what about the other side of this equation? First of all, when H3PO4 loses a proton, so it loses an H, it's going to be H2PO4, but it loses an H plus, it's no longer neutral. It has a negative charge now, which is why you don't forget that negative charge there. All right, in reverse, the proton is going to go this way because that's how you'll get H3PO4 back. So this will be the proton acceptor. So this is acting as a base. It is a conjugate base of H3PO4. Hydronium is the conjugate acid of water. They differ by a proton. Okay, so that's how that would go. And here's an interesting one. I left this one for last. So let's see if I have a couple of chats here that I should look at. Okay. Here's an interesting one. So at first glance, which way might you think that the proton goes over here? You see you have something with an H, so you might think that this is an acid. But take a look at the reaction. What's the direction of the proton? Is it going to HCO? Is it going towards this molecule, or is it going away from this molecule or this ion?
Towards?
Yes, it's actually going this way. It is accepting a proton. You can see that because you end up with H2CO3 on the other side. So here, this chemical, which is called the carbonate ion, sorry, it's not carbonate, it's bicarbonate, is accepting an H plus. It's accepting a proton, so it's a base. And water is acting as the acid. So if we go to the other side of the equation, you could see that in order to get HCO3 minus from H2CO3, you would have to donate the proton that way. And this OH minus would become water. It's accepting a proton here, so it's the conjugate base of H2O. And this is carbonic acid. You don't need to know the name, or if you did, you could look it up on that chart. This is the conjugate acid of HCO3 minus. It's called carbonic acid. Okay, so those are all the examples. So these are, very sort of basic acid-base reactions. Okay, let's see. So I have something else to tell you about these conjugate bases. I've said that acids can be strong or they can be weak. So there are two different kinds. When we have the 6 strong acids, and that's HCl, HBr, HI, HNO3, etc. Okay, these guys, HCl, for example, when they react with water, that is a one-way. Oh, that hasn't happened in a while. Interesting. All right, well, we're back. I don't know what happened there. It's a one-way arrow, and you end up with Cl minus, run out of space here, plus H3O plus. Okay, so we say that Cl minus is the conjugate base of HCl. But we actually know that it's not a base because it never goes in the other direction. Cl minus never accepts a proton from H3O plus and goes the other way. So I'm going to write here, we say Cl minus is the conjugate base of HCl, but Chloride does not act as a base. So if it did, the reverse reaction would happen. And it doesn't. So the fact that HCl is a strong acid means that its conjugate base is really not able to accept a proton. So when you have a strong acid, you have a weak conjugate base. So let me write that down. Strong acids have extremely weak conjugate bases. So they aren't even bases. They are not bases at all. We call them extremely weak conjugate bases. So a strong acid like HCl, its conjugate base is basically neutral. They are neutral. So Cl minus is neutral. It does not act as a base. What about a weak acid? So contrast this to weak acids like acetic acid, my favorite. Okay, so HOAC plus water. It donates a proton only a very little bit of the time in a reaction that heavily favors the reactants. You get acetate and H3O plus. Well, if this thing is the overwhelming reaction, so it's got way more back reaction than forward reaction, that means that this is happening a lot. This proton is going from H3O plus to acetate. This happens a lot. So here we have a weak acid with a conjugate base that's stronger than the Cl minus. So the weaker the acid, the stronger the conjugate base. I haven't proved that, but I just showed you two examples where we had a very strong acid and it has a conjugate base that doesn't act basic at all. And then we have a weak acid where with this reaction, where acetate is acting like a base, happens all the time. So the weaker the acid, the stronger the conjugate base. Okay, so there's really no contest between acetate and chloride. And I have a chart here. This is also in the, let me move it up a little. This chart is it's in the activity handouts for this unit. And what it shows, right. So what we have here is we have a list of acids, HCl, for example, strong acid. And you could see that the acid strength increases as you go up. So the ones on top are strong acids, sulfuric acid, nitric acid. These are strong acids. And their conjugate bases, you could see all that, the relationship between the acid on the left and the base on the right. So the acid on the left has the H plus, the conjugate base on the right does not have the H plus. So we have HCl and Cl minus. We have H2SO4 and HSO4 minus. We have HNO3 and NO3 minus. And notice on the left, we have the base strength. Base strength is increasing going down this way. Chloride, notice it says negligible. That means it has negligible, Cl minus has negligible, which means nothing, has negligible base strength. In other words, not a base. Does not act as a base. And let's see, here is acetic acid, right? That's one of the many aliases of acetic acid, HOAC. Okay, and you could see its conjugate base to acetic acid. This is acetate. It is much further down the base strength list, right, than chloride. So the stronger the acid, HCl is way stronger acid than acetic acid, but OAC minus is a much stronger base than chloride. So this just gives you that idea. The weaker the acid, the stronger the conjugate base. The stronger the base, the weaker the conjugate acid. Okay, that's what this chart is indicating here. All right, so the next thing I'd like to talk about is something I think is going to look a little more familiar to you because it's all about equilibrium, and we've studied equilibrium. So let's talk about quantifying. How do you put a number quantifying acid strength? So how can we tell when that one acid is stronger than another acid? Okay, so here's a kind of, I'm going to write what I'm going to call a kind of a generalized acid dissociation reaction. And many times with this, they call an acid HA. Okay, and it's understood that this is the H, that's the H that the acid is going to lose. So if you start with HA in a reaction with water, that proton would be donated. And you would end up with the rest of that. That's A minus. If it was HOAC, it would be OAC minus. And H3O plus. So if you had HOAC, this would be OAC minus and H3O plus. If you had HCl, Cl minus and H3O plus. So that's what I mean by a generalized form of this, except the HCl would be a single arrow, wouldn't be a double arrow. Okay, so all this aside, if we just have this HA plus water goes to A minus plus H3O plus, how do we quantify the strength of the acid? Well, the strength of the acid has to do with how far forward does this reaction go? The further it goes to the right, you know, the stronger the acid is. And what number do we know that characterizes how much an equilibrium goes to the right? That the number is the equilibrium constant. Okay, let me get rid of this thing. Okay, so how far forward does this reaction go? To get at this, look at Kc for this acid dissociation reaction. Okay, so if we have this reaction, what is the Kc? It's the concentration of A minus times the concentration of H3O plus over. Now remember, water is a liquid here. I haven't written it in, but in every one of these reactions with water, the phase of water is liquid. These other phases are aqueous. So they will all appear in the equilibrium constant expression, but the H2O will not. Okay, so that is Kc for this reaction, and we call it Ka, the acid dissociation constant. So the acid dissociation constant is just the equilibrium constant for an acid dissociation reaction. That's all it is. Okay. And the fact is that the greater the value of Ka, what do I put in here? Stronger or weaker? The stronger the acid or the weaker the acid? Remember, you have products on top here. The greater Ka is means you have more products. That would mean you have a stronger, yes, a stronger. The stronger the acid. Okay. So let's talk about acetic acid again, just a little bit. HOAC plus H2O. Now I'm putting in the phases. I'm not being so sloppy. H3O plus OH minus. Oops, sorry, not OH minus. OAC minus. Okay. And the Ka is this, A minus H3O plus over HA. And the value is 1.75 times 10 to the negative fifth. Okay. 1.75 times 10 to the negative fifth. That is not a very impressive number as far as forming a lot of product. Quite the opposite, okay? What this means, this is a small number. This is pretty much a lot less than 1. And so what that tells us is that there is really very little H3O plus at equilibrium. Very little acetate as well. And there's lots of undissociated acetic acid. Okay, so it's an acid, but in that solution, there's really very little H3O plus. If I take a look at some other weak acids, for example, HNO2. HNO3 is a strong acid, but HNO2, which is nitrous acid, is a weak acid. And its Ka is 4.5 times 10 to the negative fourth. So it's a weak acid, but it's stronger than acetic acid because this number is greater than 1.75 times 10 to the negative fifth. Okay. Another example is this acid is called hypochlorous acid, and its Ka is 3.5 times 10 to the negative eighth. Okay, this is also a weak acid, but it's really much weaker than HNO2 or HOAC. And that's because it's got a smaller Ka value. So the value of Ka is actually pretty important. And let me tell you, there is a very wide range of these Kas, okay? So I'm just going to show you again. I showed this to you once or twice already. This chart, which is the acid dissociation constant chart. Let me see if I can bring it up a little. I don't know why I do this to myself. I should just leave it where it is. All right, so here's a chart of dissociation constants of acids. You could see the exponents here are all different. Here is, let's see. What's this? What's going on here? Here's one. This is 1.1 times 10 to the negative 2. This is about the strongest weak acid you're going to get. I think there's another here. This one's a little bit stronger. This is strong for a weak acid. Here's another one, 10 to the minus 2. Okay. Then there's ones that are really very, very small, like this one, 10 to the minus 10th, 10 to the minus 11th. You can see there's a big range. Look at this one, 10 to the minus 13th. Okay. So these are very weak acids. These ones in blue. And the stronger weak acids are in red. In fact, some of those blue ones are not even acids, but we'll get to that later. Okay, I do want to encourage you to look at this table, to get familiar with this table. And I really would like you to think about this table as, you know, your best friend in this unit, okay? So if you're doing a problem and you don't know if an acid is strong or weak, you could look at this chart. If you don't find it on the chart, then you can assume it's a strong acid in my class, okay? Because all the weak acids that I ever ask you about are on this chart, all right? I also want to tell you that if I'm giving you a problem, let's say on a next exam or something, or in a graded assignment. Oops, what did I do there? I think I just stopped sharing by doing something. That was dumb. How do I fix this now? I don't know what happened there. So if I give you a problem and I ask you to solve it and you need to look up the Ka for a weak acid, please don't look on the internet, because some of these numbers on the chart, you know, you look in one reference, it gives you one value. You look in another reference, it gives you another value. Please use these values for my problems, okay? Because if you use a different value, then I have to calculate it with a different value. And it's a lot of extra trouble for me. So please don't just go looking up Kas on the internet. Use these values in this chart. It's in the activities handout. And it actually is, you know, we just look the number up. It's easy. And that's what I want you to do. Okay. All right. So let's see. Let me see what I'm going to talk to you about next. All right. I'm going to tell you about a Ka for a strong acid. Now, usually, you know, we don't even mention Kas for strong acids. I'm just going to give you an example. Here's one. HBr plus H2O goes to H3O plus bromide. This is a strong acid. So I tell you it's a one-way arrow, but you know, that's an approximation. It turns out that there actually is a Ka for this. And soon you'll know why we don't bother telling you about it. It's because it's so enormous. This is a liquid, doesn't count. This number is about 10 to the 9th. It is so big that it really goes to completion. So when you have a strong acid, you can safely assume that there is no back reaction. Okay, so if you take another strong acid, HCl, and let's suppose you dissolve enough HCl to make, HCl, by the way, is a gas, So you dissolve it, you take a tank of HCl gas and dissolve it in water. Normally what we do is we make a concentrated solution, and that's how it's sold. But that's literally a dissolved gas in water. And then you would dilute that concentrated solution. So let's suppose you dissolve enough HCl or you dilute a concentrated HCl solution to make a 0.050 molar HCl solution. Okay, so I have a bottle, and on the bottle, it says 0.050 molar HCl solution. And honestly, you don't want to, well, 0.050 isn't that strong, but you probably want to deal with this in the hood because the odor of HCl, 0.05 isn't so bad, but if it was like 5 molar, you would definitely want to work with that in the hood because it has an awful odor. Okay, so this is what it says on the label, 0.050 molar. So I'm asking now, if that's what's on the label, what's actually in the bottle? Sometimes I jokingly say, what's in the soup? You know, are there HCl molecules in the bottle? There are actually none. HCl reacts with water to give Cl minus and H3O plus. It is a one-way arrow. So if I have 0.050 molar HCl, it's labeled that on a bottle, but there are actually no HCl molecules inside that bottle. So what's actually in the bottle? The answer to that. Well, maybe you can help me with that answer. Okay. Oh, sapling. Somebody asked me, what about the Ks for sapling problems? Sapling problems, they supply their own Ks. So yes, you better be self-consistent with sapling. So you can always get the Ka by looking at the information. So if you use mine, you might actually get the wrong answer on sapling. But for my problems, you got to use my values. Okay, good question, actually. I have to put the sapling up for that unit. Anyway, so what's actually in the bottle of 0.050 molar HCl? Is there any HCl? So I should say, are there any HCl molecules? And what's the answer to that?
No.
No. I don't know. Did you say no? I couldn't hear you very well. Okay, so what is there is you have chloride ions and H3O plus ions. And what is the molarity of chloride ions that you have in the bottle? If you start with 0.050 molar HCl, you end up with 0.050 molar Cl minus and 0.050 molar H3O plus. It completely converts so that there is 0 of this left. So what's in the bottle is this. Okay, the same concentration as what you started with. In HCl, you now have in chloride, and more importantly, for acidity purposes, H3O plus. Okay, so what is this? I thought I got rid of that already. It's pretty dumb. Okay. All right. So if you have 0.0125 molar HCl solution, this has 0 HCl molecules. It has 0.0125 molar H3O plus and 0.0125 molar Cl minus. Okay. Doesn't matter what the concentration is, it all gets converted over to those ions. Okay, so now we have this activity 2. Okay, so just like in the previous example, what this is asking is about a 0.5 molar HCl solution. So what is the concentration of actual HCl molecules? in the solution? What's the answer to this question here?
Zero.
That's right. And what is the concentration of H plus or H3O plus in that solution? It's not a trick question.
0.5.
That's right. And what is the concentration of Cl minus in that solution?
0.5.
That's right. Okay, now I'm going to introduce you to a quantity called the percent dissociation or percent ionization. And this is what it is, just like it's written above there. It's the concentration of H3O plus in the solution divided by the initial concentration of acid. So that initial is 0.5 molar. That's what you started with, okay? That's what goes here. And now you put the concentration of H3O plus in the numerator. So what you can see is that in the case of a strong acid, like hydrochloric acid, this is, if you multiply this, this is, I should have written times 100. So this is 1 times 100 or 100%. So we say that HCl is 100% dissociated. So strong acids like HCl are 100% dissociated. So you don't even have to do the calculation. If it's a strong acid, it's 100% dissociated, nothing to calculate. Okay, that's the easy answer, the easy part. Weak acids. It's not as easy. It's not as easy to figure out the percent dissociation. It's also not as easy to figure out how much of the H3O plus you have in that solution. Okay, weak acids are much more interesting. Okay, if you dissolve enough acetic acid, let's say, just like we did with the HCl, so this is acetic acid, to make a 0.5 molar solution, okay, what's the concentration of H3O plus? How can we answer this question? Okay, how are we going to figure that out? How to figure this out? Well, you know, in the case of HCl, if we go back, you know, this is a one-way arrow, okay, right here. In the case of acetic acid, it is not a one-way arrow, okay? We have a reaction like this. And we have a Ka. Oh, look at this. So we're going to have to set up an ice chart to figure out the concentration of H3O plus. So here's an ice chart. Okay, my initial concentration is 0.5 molar, right? Because that's what we're working with here, 0.5 molar. Okay. Liquid, I don't have to put a liquid in the ice chart. And now initially I say, I have no products. Let's say this hasn't happened yet. The dissociation hasn't happened yet. So I set up my ice chart. I say, okay, let X be the amount of OAC that reacts. And that's going to be the same as the amount of these that are produced because all the coefficients here are 1. Okay. then at equilibrium, I just have to add these up. So I end up with x squared over 0.500 minus x equals, so what is that equal to? It's equal to the equilibrium constant, which is the Ka, which is, let me just write in what it is. Ka is 1.75 times 10 to the negative fifth. So 1.75 times 10 to the minus fifth. So I have this equation here, and I need to solve this to get x. So how would I do that, right? This is one of those cases where you have a cross multiply, you have a quadratic, you'd have x squared equals 1.75 times 10 to the minus fifth times 0.5 minus x. So you'd have to multiply this out. You'd get 1.75 times 10 to the minus fifth times 0.5 minus 1.75 times 10 to the minus fifth x. It's kind of a pain in the neck. Okay, you would group all your terms. I'm just going to write et cetera, et cetera. Okay, when you do this, and now you solve the quadratic, you end up with that x is 0.00299. Okay. So that would be the concentration of H3O plus or OAC minus, right? Because if you go back, you see these concentrations are X. Okay. So, you know, we could solve the quadratic, but let me tell you that in most acid problems, there's an easier way. And the reason that there's an easier way is because that K, that Ka, that equilibrium constant is really small. And what we can do in many cases is we can actually simplify the equation that has to be solved. So if you notice here, let's actually, if this is our X and this is H3O plus and OAC minus, what is the HOAC concentration at equilibrium, right? It's going to be 0.500 minus X, which I know if I go up here and look, there it is. So 0.5 minus 0.00299, I'm not subtracting a lot. This comes out to 0.497. So it's almost equal to what it started out as, 0.500. Okay, so I know that this X is going to be very small. And in fact, you could see it is very small. And so what you can do is you can actually neglect the X in this equation. So we had, this is the equation we solved. X squared over 0.5 minus X equals the Ka. So we had x squared over 0.5 minus x equals the Ka. Okay, so the thing is that x is so small compared to the initial concentration. And that's because the Ka is small, because this reaction does not go forward very much. So because X is so small, we can, in many cases, so in many acid problems, neglect it in comparison to 0.5. So 0.5 minus X actually becomes just 0.5. So I had 0.500 minus X. If I neglect the X, this is approximately equal to 0.5. And I know I'm a little bit wrong because I know that that's actually 0.497, okay? But I'm not that far off. But what I have to do is I have to tell you what criterion we use to neglect X. So the criterion for neglecting X in acid problems is this, okay? You can neglect the X if the initial acid concentration, so in that case, this case it's 0.5, is greater than 100 times the Ka. So you have to ask yourself the question, is 0.5 greater than 100 times 1.75 times 10 to the negative fifth, which is 1.75 times 10 to the negative third. Is 0.5 greater than that? 0.00175. Yes, it is. So we can neglect the X. Okay? All right. I don't know why I didn't give myself more space here, but okay. So how do we solve this problem neglecting the X? Well, it's so much easier. So we have HOAC plus H2O goes to OAC minus plus H3O plus. Okay. And we had this already set up. This was 0.5 minus X at equilibrium. This was X squared over 0.5 minus X equals the Ka. All right, so now, instead of having this negative X here, we cross it out. We simply neglect it. And the problem that we solve instead is this. Well, that means when you cross multiply, right? There's no minus X in here to worry about. And we could solve a much simpler equation right there. Okay. And we end up with, if we multiply these two together, we get 8.75 times 10 to the negative 6th, I guess, equals X squared. And just take the square root of both sides. You end up with X is 0.00296. So remember the true value of X from solving the quadratic is 0.00299. So this is pretty close. And that's what we do when we solve these problems, but you have to use the criterion that's given here. And in fact, if you use this, if you neglect X in a problem, you have to put the justification there. So not only do you need to say, you actually need to do it for your particular problem. You need to go through what I did above there. Right, so I actually figured out what 100 times the Ka was. And I showed that, yes, indeed, 0.5 is greater than 0.00175. So to neglect X in a problem, you must include the justification, and you must figure out what the initial acid concentration is and show that it's greater than 100 times the Ka. So you have to calculate this, which is easy. Just multiply by 100 for your problem and include it. That's a justification. All right, so we can now fill in the answers here to this rest of activity 2. What is the concentration of HOAC molecules in the solution? Well, we had X is 0.00296. The concentration of acetic acid is 0.500 minus that. It really doesn't matter if you had a 9 here. It's still to 3 decimal places. It's still going to be 0.497. So that's what we put here. Okay. What is the concentration of H3O plus? 0.00296 molar. Acetate, that's also X, right? 0.00296 molar. And now the percent dissociation is a more interesting calculation here, right? It's the concentration of H3O plus over the initial concentration of the acid times 100. So it's 0.00296 divided by 0.5, right? That's the initial, not the 0.497. And that comes out to, look at this. Man, that's such a small percentage that you might think, oh man, how is this thing acting as an acid? But it's enough to make it an acid, all right? It does produce H3O plus, just not a ton of it, okay? All right. How's everybody doing? I want you to look over your notes, see if you have any questions, and bring them out now, because I'm going to turn the page a little bit and start talking about pH. So take a couple minutes to look over your, your stuff. Do you have a question? Did I go through something too fast? Kayla, you got any questions? Okay, good. Well, all right. Not right now. Okay. All right. Anyone else? Okay. So I'm going to talk about pH, but what I have to actually talk about first is acidity. Okay, so acidity is actually the concentration of H3O plus ions in a solution. So, if I have like the solution I had here, the acetic acid solution, its acidity is 0.00296 molar. That's how many H3O plus ions it has. So just to talk about the types of concentrations of H3O plus that can be in a solution, typical concentrations of H3O plus ions. There is no typical value. That's why I put it in quotes. They vary all over the place. So for example, if I have neutral water, the H3O plus concentration is 1 times 10 to the negative 7th molar. If I have a strong acid solution, for example, I might have 1 molar HCl. That has 1 molar H3O plus. We know it completely dissociates. It has 0 HCl. It has 1 molar H3O plus and 1 molar chloride, but who cares about chloride? It doesn't do anything interesting. If we have a strong base solution, if we have 1 molar hydroxide, like NaOH, we haven't learned this yet, but we will do it the next time, that concentration would be 1 times 10 to the negative 14th molar of H3O plus. So look at this. We have this enormous range of possible concentrations, possible acidities, different acidity values. And what the pH scale does is it actually sort of compresses all acidities from 1 molar to 10 to the minus 14th molar into a 0 to 14 unit scale. Okay, and we call that the pH scale. Okay, so what this scale, what the pH scale is based on is, okay, let's suppose we wrote these concentrations in scientific notation. I'll fill this in later. If the concentration of H3O plus is 1 times 10 to the 0 power molar. So it's really, 10 to the 0 is 1. 1 times 10 to the 0 molar. So it's 1 molar. Then the pH is 0. The pH is based on the exponent when you write your H3O plus concentration in scientific notation. If the H3O plus concentration is 1 times 10 to the negative 1 molar, that's 0.10 molar, then the pH is, okay, it's 1. Let me just give you one more example. If the H3O plus concentration is 1 times 10 to the negative 7th molar, 1, 2, 3, 4, 5, 6. So that concentration, the pH is 7. So do you see a pattern here? Okay. If you write a concentration of H3O plus and it's 1 times 10 to the something, then the pH is the negative of that something. Okay, that's the pattern. So I hope that, so, I mean, it makes sense. It's that this is based on the exponents when the H3O plus is in scientific notation. And, and that's not a shock or surprise, because it's based on logs, base 10 logs. In fact, the pH is the negative base 10 log. This is different from a natural log. It's different because the inverse of this is 10 to the, as opposed to e to the, okay? So it's the negative log of the H3O plus concentration. Okay, so if you write your H3O plus concentration, if this concentration is 1 times 10 to the something, right? Some power, then the pH is the negative of that power. Just like I showed you here. If the H3O plus is 1 times 10 to the negative 7, the pH is 7. If it's 1 times 10 to the minus 1, the pH is 1. All right, so you might justifiably ask the question, what if you don't have a number that starts with 1? Okay. Well, to take care of that, you have to use your calculator. All right. For any other numbers, so let's say you have 4.5 times 10 to the negative 3rd. Okay. You have to use your calculator. So if this is the H3O plus concentration, you simply take the log of that number and it is is, try it out on your calculator. Negative 2.347. You take the negative log, so you change the sign. So the pH is 2.35. And actually, we have different sig fig rules. This has 2 sig figs, so it's 2 sig figs after the decimal place. That's why I only kept 2 there. But that's something for that we will get used to as we go along. Let's see. So I have a little chart here. No, that's not it. Here's the chart. All right, so what this chart is showing is what I just said. When you have a strong acid, first of all, you have full dissociation here. This is a little bit of review, full dissociation. So if you have 10th molar HCl, that's 1 times 10 to the minus 1 molar. That's going to be a pH of 1. Take the negative of that exponent, and that's what it is. If you have 0.01 molar HCl, 1 times 10 to the minus 2, that's a pH of 2, and so on. Okay, this is the definition that we already used. All right. So if you have a number that's not 1 times 10 to the something, of course, you're going to use your calculator. But, you know, sometimes your calculator doesn't really give you the number. You know, maybe you press something wrong on it. So I want you to be able to have a feeling for what number you should get when you take the pH of a number. So I have this exercise here. This is activity 3. And I just, you know, put up with this for a little bit. Suppose you know that the H3O plus concentration is 0.0057. Okay. You can ask yourself, you know, can I put brackets around this? Can I say that this is between 2 different powers of 10, like 0.0057? Which of these 2 numbers is that in between? It's between 0.001 and 0.01. All right. So 0.001 is 10 to the negative 3. 0.01 is 10 to the 0.01 is 10 to the negative 2. So since I have bracketed this number to be between these 2 numbers in terms of powers of 10, that means that my pH will be between 3 and 2, the negatives of those numbers. So I know that when I take my 0.00757 and put it in my calculator and find the log of it and then take the negative of that, so take the log of that. So the log of 0.0057 is negative 2.24. So now the negative log is 2.24. Okay, so it's between 2 and 3. I knew it was going to be between 2 and 3. So if my calculator gives me 10.57, I know I did something wrong on that calculator. So that's why I give students this exercise to do, because it doesn't take very long, and it sort of gives you an idea of what pHs will be like when you have certain H3O plus concentrations. But I do want to mention this little detail here, which is about significant figures. And here it is. When you take the log of a quantity, so then you get a log, the number after the decimal point in the log will equal the number of sig figs in the quantity. So over here, let's take a look. We had 0.0057. We had 2 sig figs in the number. We keep 2 sig figs after the decimal place in the log, so in the pH. And that's a somewhat different sig fig rule that we use. And I'll go over it again with these next examples. So which two numbers should I say? Okay, we have 0.01880. And what's that in between? It's between 0.01, but it's a little bigger than that, right? Because it's got other stuff after it. So it's between those two. So it's bracketed. And this is 10 to the minus 2 and 10 to the minus 1. So that's what this is in between. So the pH would be between 2 and 1. And now when you use your calculator to take the log of 0.01880, and you do that, you get 1.7258. You see that it's between 1 and 2. Now, how many sig figs do I keep? Well, in the quantity, I have 4 sig figs. So in the log, I keep 4 after the decimal place. Oops, I just lost one. All right, that's enough. Enough said for today. I'll start with this next time. So I just want to make sure.